Hello, and welcome back to another IB Math CodingBytes speedrun with me, Vince. In this speedrun, we're going to be finishing up the final exercise in chapter 1.2, and that will be all for today. I don't think I mentioned this earlier, but what I'm actually trying to do is I'm trying to finish one subchapter a day for every day until I finish this math book. And so I hope that makes me study better, and it also makes me upload more of these videos so you guys can also, learn more with me in the process. So let's get to the final subchapter. So the first question we're going to look at is this one. We're actually going to start from number 2 this time, and as usual, we're going to be skipping every other question, so that you guys also have some questions that you can practice on yourselves and make sure that you know the content. So, Jane started working in 2000. On each successive year, she received a salary increase equivalent to 1.5% of her previous salary. In 2011, her salary was $49,650. It was $49,650. Determine her starting salary to the nearest dollar. Okay, so this is a question of geometric sequences. We know that the common ratio is equal to 1.015, because every year she receives a salary increase of 1.5%, and this is 100.15%. So this is the common ratio between all of her salaries. So since in 2011 her salary was $49,650, and we want to determine her starting salary, we can simply divide 49,650 by 1.015 to the power of 11, I believe. And this will give us, let me just punch this into a calculator, 49,650 divided by 1.015 to the power of 11 is equal to $42,150. I think that should be it, but let me just quickly check that we've got the answer correct. And where is it? Hold on a second. It's a long book, taking a long way to wait. Okay. Anyways, are we correct? Yep, we are correct. So let's move on to the next question. Oh, that erase. Okay, now let's move on to the next question. So we have the fourth question. Prisana is testing a recipe for a cake and tries it out several times, adjusting the amount of flour and sugar used each time. In the first recipe, she uses 200 grams of flour, and she decides to increase the weight of flour by 20 grams in each trial. She has time to try out the recipe just 10 times. How many kilograms of flour would she need? Okay, so We can get a very simple series from this. As we can see, our starting term is 200. And our common ratio is 20. In this case, our common difference, since it's an arithmetic sequence, is 20. So we need to get the sum of the first 10 terms. And the sum of the first 10 terms will be equal to, what is this? The 10 divided by 2 times the 2 times the first term, 200, plus n minus 1, which is 9 in this case, times d, which is 20. So this is equal to 5 times 400 plus 180. Otherwise, this is 580, so it will be 5 times 580, which is equal to some back of the envelope math. Looks like 2,900. Yeah, 2,900, if I'm not mistaken. Let me just check that. 58 times 5, yeah, it should be 2,900. And so this is in grams. And so, of course, we need to convert to kilograms. So 2,900 grams is equal to 2 kilograms. So this is our final answer. Yeah. Okay, there's another question apparently linked to this question. So I'll add it to the end of this. So she has 1.5 kg of sugar available and knows that the amount of sugar needed is usually half of the amount of flour by weight. It should be mass, but this is math, not physics. If after the first 2 trials, she decides to change the amount of sugar in each trial according to a geometric sequence. Evaluate the number of trials this would allow her to carry out. Explain how reliable her model is for using a geometric growth model for sugar content. And let me just move this to a different area so we can see it a bit better now. All right. So, now we need to solve it. We know that the first 2 trials will be half the amount of flour by weight. So the first 2 flour trials will be 200 and 220 grams respectively. And so half of this would be 100 and 110. And since we're using a geometric model, this means the common ratio would be the difference between the 2. So this would be common ratio is equal to 1.1, and our first term is 100. And we need to, she has 1.5 kilograms of flour, and we need to check how many trials she can run. So we can say 1,500 is equal to the sum of the series, and remember the sum is equal to the first term times 1 minus the common ratio, 1.1, to the number of terms, in this case is n, divided all by 1 minus the common ratio, which is 1.1. So in effect, we have 1,500 times, what's 1 minus 1.1? That's 0.1, negative 0.1. And that's equal to 100 times 1 minus 1.1 to the n. So negative 150 is equal to 100 minus 100 times 1.1 to the n. Otherwise, this should be 250 is equal to 250 divided by 100, which is also just 2.5. So 2.5 is equal to 1.1 to the n. So we can simply take the logarithms of both sides. So we can have log 1.1, 2.5 is equal to n. And therefore we get the number of trials to be, if I can just get a calculator, should be, where's the logarithm button? Logarithm button, and we have 2.5 divided by logarithm of 1.1, and your answer should be something like 9.6, something around 9.6. And so this means she can do only 9 trials successfully. Now, commenting on whether this model is a good model for growth, I would say it's okay, because, I would say it's not that reliable, because if you think about it, this is a geometric growth, and when the cake gets bigger by a certain amount, it's getting exponentially more sweet. And so eventually the cake would end up being, a majority of just sugar. Let me check if that's right. Yeah. So, yeah, it also says, in fact, the ratio of sugar to flour would eventually become 1 in the unrealistic case that the trial is carried out a large number of times. So, yeah, that is correct for this question. So, move on to the next question. So we have a guy called Yu-hun takes out a loan of $1,500 to furnish his new student apartment. The terms of the loan are that he will pay equal monthly installments. Interest is calculated monthly and is charged at 12% per annum, so this is per year. The loan is to be paid in 2 years. Okay, so we need to calculate the amount that Yu-hun has to pay each month if the first repayment is made 1 month after the money is borrowed and after interest is calculated. And B, evaluate how much to the nearest dollar Yu-hun actually has to pay. Okay, so it looks like we've been set up with a geometric sequence. The interest is 12% per year, which conveniently makes it 1% per loan payment, since we're dividing the interest equally among the loan payments. It means the common ratio is equal to 1.01. And I'm going to assume this is compound interest because we're in IB and simple interest is for kids. So, we need to calculate the amount Yu-hun has to pay each month. Do we have to calculate it for every single month? Or do we just have to calculate it for the first month? I think we just have to calculate it for the first month. So 1,500 divided by 2 years, which means 24 payments. So 1,500 divided by 24 is equal to the number of payments. So let's just see how many times he has to pay it. 1,500 divided by 24 is equal to 62.5 times. Oh, sorry, $62.5, I should say. And I don't really get this question, honestly. There's no way you have to calculate it each month, right? So the first month should be 62.5 times 1.01, which is equal to 62.5 times 1.01. It's like 63.13. And I guess let's calculate just how much it will be at the end. I don't feel like calculating every single month, and I feel like it will also be a waste of time. So to calculate the amount of money he will have to pay at the end, it's just 1.01 to the power of 24. So this should be 62.5 times 1.01 to the power of 24, which adds up to around 79.35. Check the mark scheme. What does it say? It says 78.4. Okay. He will pay equal monthly installments, and then the interest is calculated monthly and charged at 12% a year, and the loan is to be repaid at 2 years. Okay, maybe it is simple interest, and maybe they're clowning around like kids, honestly. So 12% a year works out to be 1,500 times 1.12, and sorry, of course, 1.24, and this would be, see, 1,500 times 1.24 is like 1,860, right? And we simply divide that by the 24 months and get 77.5. You know, okay, what I think they're doing is, I think what we actually need to calculate is its compound interest per year. So this would be 1.12 to the power of 2, which would be equal to 1,500 times 1.12 to the power of 2, which is equal to 1881.6. And if we split this per month, 24, 1.6 divided by 24. Okay, we finally get the correct answer, which is 78.4. So this is like a weird method, I guess. So it's compound interest per year, and we're splitting it in, I guess, equal monthly installments. It's just a very weird question. How much he has to pay to the nearest dollar? Well, we literally have it here, 1881.6. Is that correct? Yeah, it is. Well, 1882, because it's to the nearest dollar. And so that was a very weird question, but okay. Next question. So we have Isla, Brenna, and Cindy each receive $200 from their parents with the condition that they promise to invest it for at least 10 years. Isla invests her money into an account that offers 5% simple interest annually. Brenna says it is better to invest into an account with compound interest, so she invests her money into a bank with 3.5% compound interest compounded annually. Cindy is not sure, so she invests 100 into Isla's bank at the same 5% rate, and 100 into Brenna's bank at the same 3.5% compounded rate. So first, evaluate how much investment each investment is worth after 10 years. B, how much is each investment worth after 25 years? And C, determine after how many years the three investments yield approximately the same amount. Okay, sure. So I guess let's start with A. ILS is pretty simple. 200 at 5% simple interest. Well, what's 5% simple interest of 200 times 0.05? And that will be equal to $10 per year. For 10 years, that's $100. So she'll earn $300 by the end of this. Cindy, well, that will be 200 times 1.0. I mean, this I guess could be 1, but anyways, 200 times 1.035 compound interest to the power of 10, because it is compounded each year. And that would be, get a calculator. 200 times 1.035 to the power of 10, which is equal to $282.12. So a bit less than Isla's. And the last one, Cindy, well, I mean, here's a cheat. We can just divide both of these by 2. So her investment will be equal to 150 plus 141.06, which is equal to 291.06. And yeah, I think those should be the correct numbers. Let's just check they are. 300, 282, 291. Yep. Okay, after 25 years, it gets a bit more. Okay. So you have Isla 200 times, it's just 200 plus 10 to the times 25, which is equal to $350 then. Cindy would have 200 times 1.035 to the power of 25, which the compounding starts to get significantly better. And she has a result of $472. And of course, this is Bryn. And finally, Cindy has the average, which would be 175 plus 472 divided by 2. It's like 236. And that would be equal to around $411. Oops. So we can see that in the long run, compound interest is better. So finally, we want to determine after how many years the 3 investments yield approximately the same amount. And to do this, we just need to figure out how many years it takes 3.5% compound interest to equal 5% simple interest. Yeah, so 1.035 to the power of n is equal to 1.05. And that's about it. So we have log 1.035, 1.05 is equal to n. How many years will it take? Let's test. I don't think we can do that. I think that's cheating. Okay. Let's stop cheating and let's write it out the full way. So we want to check when the investments will equal. So 200 times 1.035 to the n is equal to 200 plus 10n. Remember, because this is simple interest, 10 is 0.5% of 200. So we have 1.035 to the power of n is equal to, how would we equate these variables? I guess the straightforward way is taking the log. So let's think. 1.035. If we take the log of this, we have n here, but we also have n here. And we kind of don't want that. I mean, we could use recursion, but I don't want to do that, and I feel like there's an easier way to do this. Okay. So first let's just divide everything by 200. So 1.035 to the n is equal to 1 plus 0.05 n. Okay, this looks a bit better. So log, fine, n log 1. I guess we have to do it this way. Log 1 is equal to 0, of course. So this will equal to log 0.05. Is this the best way to do it? I don't know. Oh, sorry, no, this is like, oops. I don't know if this is the best way to do it. I mean, I guess we could use recursion. And so,
Are you recording?
Yeah. I mean, okay. I've decided that we will do it the old-fashioned way of simply trial and error. And I think there are better ways to do this than that, but this will suit our needs fine. If you have a TI, of course, you can just punch this into the solve function for you, but if you don't, then I'll just do it this way first. So when n equals 1, we have 1.035 is equal to 1.05. Of course, it's not. When n is equal to 2, we have 1.035 squared. So that's 1.071 is still less than 1.1. Well, when we have 1.035 cubed, we have 1.109, which is still less than 1.15. When we have 1.035 to the power of 4, we have 1.14, 1.148, which is still less than 1.2. When we have 1.035 to the power of 5, we have 1.19. 187 technically, which is still less than 1.25. When we have it to the power of 6, well, we have 1.229, which is less than 1.3, but we're getting a bit closer. When we have it to the power of 7, well, we have 1.272, which is less than 1.35. Hello, sorry about that. So this is actually quite a long problem, and through the really bad trial and error method, I finally got an answer at, this is, as you can see from this side, sorry, 2.05. This is the 21st year. So after 21 years, the compound interest produces more money or return on investment than the normal fixed interest. But this method was clearly not a viable solution, so I'm going to show you the alternate way to do it using a graphical calculator. If you have a graphical calculator, you want to plot the graphs of both 1 plus 0.05x, which looks something like this, and what is the other one? It's 1.035 to the power of x. And you will get two intersections. One is at 0, because obviously if both of these are 0, then their y value is equal to 1. But the other intersection is when x is approximately equal to, I think, 20.3 something. And this will be your other answer. I don't think there is a good algebraic way to solve this problem, so I would either do trial and error, but if you don't have enough time for that on the test, then you definitely want to try something like this, where you graph it. Okay, on to the final problem of today. So, our problem is that we want to, where is it? We are a pharmaceutical company has developed a drug that fights a bacterial infection. The drug is to be administered 4 times a day, every 6 hours. It was found that 6 hours after administering 37.5% of the original amount was still in the bloodstream. The maximum safe level of the drug in the bloodstream is 8 milligrams per milliliter. Yeah. So we want to construct a model to represent the amount of drug in the bloodstream at the end of day 1, immediately after the 4th administration. Okay. So I think what they want us to assume is that this drug, once injected, decreases in some sort of exponential curve, so that after 6 hours, only 37.5% is left in the body. And so that's okay. So we know that it's administered 3 times before, and let's just say that 37 point, okay, in the 4th administration, of course, 100% of that administration will be in the patient. In the 3rd administration, from which it has been 6 hours, 37.5% of that is left. And from the 2nd one, which was 12 hours ago, only 37.5 squared, or Otherwise, this would be 14.065. So let's just write them out. 100, 37.5, 14.0625, and finally 37.5 cubed, which is 5.2734. And we have to add all of these up. I guess we could have done it using a geometric sequence, but right now let's just add them all up. And we get 100 plus 37.5 plus 14.0675 plus 5.2434, and it's around 156.8% of the drug, of the dosage of the drug is in the bloodstream at that time. Yeah. And so we've got that correct. Next. The company advises that the drug should not be administered for more than 10 days. Evaluate the maximum amount that should be administered to ensure that the amount of drug in the bloodstream doesn't exceed the safety level. Okay, so I mean, what I think we have to do more or less is just get some of the first 10 terms and make sure that's less than the 8 milligrams they specified. So we know the common ratio between terms is equal to, it's only 37.5% of the original, so this would be 37.5 divided by 100. It's the common ratio, and the first term is obviously 100. Actually, no. We don't know the first term, because the first term will be the amount of initial blood we inject, but we do know the number of times, and it's 10 times 4, since it's administered 4 times each day. So, to get the sum of this, after 10 days, it's equal to the initial dosage, and we know, this should be at most 8, is equal to the initial dosage times 1 minus 0.375 to the power of 10 divided by 1 minus 0.375. So we have 8 times 0.625 is equal to, divided by 1 minus 0.375 to the 10 should be equal to the initial dosage. So let's punch that into a calculator. We have 8 times 0.625 divided by 1 minus 0.375 to the power of 10. And we get the initial dosage should be around 5 milliliters. Let's check if that's correct. 5 milligrams. And that's correct. And, okay, so the final thing we need to do is the drug starts to being effective when the amount of drug in the bloodstream is 7 milligrams per milliliter. Determine how many times the drug must be administered for this level to be reached. I guess assuming that, we actually give this 5 milligram dosage. So, how do we get this answer? Well, we need to find, we know that the sum needs to be 7, but we don't know how many numbers, or how many, dosages we're going to give. And so that's what we're going to find out. The initial dosage is 5. And it's 1 minus 0.375 to the n, divided by 1 minus 0.375. And so we know that negative 0.375 n or 1 minus that, is equal to 7 times 1 minus 0.375 divided by 5. So let's just rearrange this so we get a logarithm. So we have 0.375n is equal to this minus 1. And so the logarithm of the base is 0.375, and we need it to be 7 times 1 minus 0.375 divided by 5 minus 1, and that's equal to n. So if we get a calculator and add all this in, we have the logarithm of long sum 7 times 1 minus 0.375 divided by 5 minus 1 over the logarithm of 0.375. And I am clearly getting something wrong because it's giving me imaginary numbers, so let's try again. Sorry, 7 times 1 minus 0.375 divided by 5 minus 1 divided by the logarithm of 0.375. And it's throwing an error. Why is that so? Logarithm of 7 times 1 minus 0.375 divided by 5 minus 1. Oh, sorry, it's 1 minus this. What am I doing? Sorry, so it should be 1 minus all of that. And let's try again. Sorry about that. So we have log of 1 minus 7 times 1 minus 0.375 and divided by 5. And we do get an answer for that, and we need to divide that by the logarithm of 0.375. And we get n as 2.12 by my mark. So at least 3 tests need to be administered before the necessary dosage is required. Before the necessary dosage is reached. So this is quite a long speed run. If you've stayed to the end, and well, I hope to see you in the next speedrun. If you like these speedruns, leave a comment down below and make sure to subscribe for more awesome content. See you!